Hello and welcome to my talk. I'm Jeffrey Covington. Today I'm going to be talking about sea ice and the problem of trying to track sea ice using satellite measurements. So before I get into the meat of the talk, I want to show a video to illustrate what I'm talking about. So here on the left, you can see satellite images of sea ice, and on the right, you can see what an algorithm has done to track the sea ice and identify the flows within the image. And these are daily observations taken from satellite imagery. And you can see that a lot of the flows can be tracked, but there's this issue where weather often obscures perhaps the image partially or almost completely, where there are almost no flows that are identifiable by the algorithm. So this talk is not going to focus on the process of actually tracking the flows. Instead, we're focused on the problem of, can you recover the missing observations due to being obscured by weather or other factors? And also, what can we use these trajectories for? So what can we say about unobserved variables in the system? For example, flow thickness or mass. What can we say about the underlying ocean or other variables like those? And also, can we quantify our uncertainty about these estimates? And so that will be the focus of the talk. So to do that, we will use data assimilation. So data assimilation combines a model with observations in order to better estimate the state of the system. So I mentioned that there will be a model. Our particular model is nonlinear because of the interaction between the ice flows, the ocean, and the atmosphere. It's also high dimensional because of all the grid points needed for the atmosphere and the ocean. And so that's going to be a real challenge for us. And it renders many of the traditional data assimilation methods unfeasible, right? It's strongly nonlinear and high dimensional. So like the normal Kalman filter will not work well because of the nonlinearity, and like particle filters, for example, will not work well because of the high dimensionality. So our chosen method is based on the ensemble Kalman smoother with a bunch of extra stuff added onto it. So, but at its core, the ensemble Kalman smoother is an iterative method. So essentially we have an ensemble of model trajectories, and we forecast that ensemble forward using our model. And then at each available observation, we update the ensemble based on the new information and then rinse and repeat, right? And we forecast the ensemble forward, update, forecast, update, and so on. So the main challenge for this particular method is going to be to reduce the computational cost of the forecast model. If we do that, we'll be able to use more ensemble members and have a richer statistical representation of the model state. So the main way that we are going to reduce the computational cost of the forecast model is to take advantage of the Fourier transform and spectral space. So our ocean model, for example, is based on the two-dimensional quasi-geostrophic equations. So they are a set of PDEs, and they describe the evolution of potential vorticity, Q, and the stream function. So we are mainly focused on the stream function. And so here's a plot of the stream function. So the contours of the stream function are the streamlines of the resulting velocity field, which will drive the flows. So the velocity field is determined by the stream function, so we will mainly focus on that. So here we can see a plot of the stream function. And if we take the Fourier transform and plot the energy spectrum, we see most of the energy is contained in the lower wave numbers. So what we can do is actually truncate the wave numbers. So only take wave numbers with a magnitude less than or equal to 11 in this particular example. And when we do that and reconstruct the stream function, we see that it looks like a fairly decent approximation. You know, like if you're only concerned with like mesoscale eddies, for example, even this rough approximation does a fairly good job of representing the function, while at the same time, it's a lot less degrees of freedom, which means easier to forecast forward. So that describes the representation of the stream function, how we can reduce the order of the model. Another way that we can reduce the computational cost is by using an approximate model for the evolution of the stream function. So how do we construct such an approximate model? So what we're going to do is take each wave number, the 5-5 mode, for example, and here is a plot of the coefficient of that wave from the actual QG model. And what we'll do is we can take the statistics of this time series, so the mean, the variance, and the decorrelation time, and we can take what's called an Ornstein-Uhlenbeck process, which is a stochastic differential equation, and fit such a process to the mean, variance, and decorrelation time. And so this approximate model matches the statistics of the corresponding mode in the QG model, except it is much cheaper to compute. Of course, the downside is that we lose the physicality, right? There will fit independent OU processes for every Fourier mode here. Of course, these are Fourier modes of the stream function, so we still retain the incompressibility. But what we gain is that this is hugely less expensive to forecast. Right, so those are the two things. One is the reducing the order through truncation, and also reducing the cost of the evolution through fitting a statistically accurate approximate model, stochastic model. Right, and to briefly go over the rest of the model, so that takes care of the ocean, is we have this approximate model for our forecast model. The atmosphere is based on the ERA5 reanalysis data set, so it's a purely data-driven model. Of course, in the future, we can add a more sophisticated atmospheric model here. But for now, it's a stochastic model based on reanalysis data. And then the ice flow dynamics are calculated using surface integrals over the area of the ice. So you can get these rich interactions between the grid and the shape of the flow. And we're keeping track of the positions and rotations of the flow. So when we take observations, we directly observe the position of the flow and its rotational displacement. And one last thing is that contact forces between flows are ignored. So there are a couple of reasons for that. One, it's very expensive, so it's convenient to, computationally expensive, so it's convenient to ignore them. Two, from satellite imagery, they're only every day. So it's really not even possible to resolve those interactions in the first place. And three, from satellite imagery, if two flows are in contact with each other, it can become difficult to distinguish one flow from another. So those are some reasons why we're ignoring contact forces. We'll address that later. All right, so let's go back to the top and go through the method. So as I mentioned before, the system state is represented by an ensemble of model trajectories. So you have the ensemble at time t, you will forecast it up to the time of the next observation. And when we're doing the forecasting, we use the forecast model. So the ocean and atmosphere are forecast in spectral space using the aforementioned stochastic, statistically accurate models. And the flow variables are forecast in physical space, right? So they're driven by the actual resulting velocity field from the ocean and atmosphere. So once we forecast up to the time of the next observation, we reconstruct the ocean and atmosphere in physical space. So we could perform the update in spectral space, but we want to take advantage of some techniques like localization, which utilize the spatial structure of the problem. And so to utilize the spatial structure, you have to convert back to physical space. So we reconstruct the ocean and atmosphere, perform the update, and then we transform back into spectral space and repeat, right? So it's this interplay between spectral and physical space. So you forecast ocean and atmosphere in spectral space and you update in physical space. And so that's really the meat of the method. All right, so let's take a look at some results. So we did two sets of experiments. In the first set, we generated artificial data with a perfect known model, right? So we generated flow trajectories with the full QG model and the reanalysis data. And then we took those observations and used and plugged them into this method with all the approximate models. And so when we did that, and when we do this, we can actually compare with known values for the hidden variables. So flow thickness, for example, we can estimate flow thickness within this framework by treating it as a parameter, right? So it'll be a non-dynamical variable that has uncertainty in it, but it doesn't change over time, right? The forecast is just keeping it constant. So when we estimate flow thickness within this framework, we actually do fairly well. So what we do is we assume a distribution of thicknesses between 0.5 meter and 6 meters. And it's a uniform thickness for each flow. And in this perfect model setup, even with a short trajectory, we can get a pretty good convergence to the, not convergence, but a pretty good estimate of the true thickness. So another thing we're interested in recovering is the ocean. So here is an experiment where we use different number of flows. So basically trying to estimate the density required to accurately recover the ocean. So the density of flows. And so here is an example where we're approaching a threshold where we can approximate the ocean fairly well. And so qualitatively between these plots, you can see this is around the 20 flow range. Between these plots, you can see that it captures a lot of the shape pretty well. Perhaps the magnitude is a bit off, but the shape is captured pretty well. And this can be important for like eddy identification, for example. So in the next set of experiments we did, we used the real data. So here we don't have access to any of the hidden variables. What we did is we took the data and we took the daily observations and we artificially removed some of the observations. That way we had something to compare to. So when we do that, we artificially remove observations, estimate what the missing observation should be, and then we can compare it to the truth. When we do that, our interpolation using the our method is comparable to linear interpolation as far as root mean squared error goes. And so in the perfect model setup, it is significantly better than linear interpolation. Once we introduce real data, it just becomes comparable. Sometimes it's better, like in the left panel here. Sometimes it's worse, like in the right panel here. That is due to the model error. So one is, of course, we're using purely reanalysis data for the wind model. For the ocean model, we're using the QG model, which itself is highly idealized. So we can improve on this if we use a more sophisticated ocean and atmospheric models using a similar way to reduce the order and create cheap forecast models. But even with just these highly idealized models, we can still get pretty good results. And so this is, even just looking at the root mean squared error, there are lots of things that linear interpolation, for example, can't do, such as giving you information about the curvature or like the velocity at different points, or like angular velocity, which has some interesting statistical properties. And so we're glad that we can do pretty well given such an idealized setup. So that's all I wanted to talk about right now. I would like to thank my co-authors and my funders, and of course the Ocean Sciences meeting for hosting me. Thank you for coming to my talk.